Okay, so today we'll discuss about application of first law of thermodynamics. Okay, so one of the very important application of first law of thermodynamics is heat engine. Okay, so heat engine is an example of application of first law of thermodynamics. Okay, it's not exactly application like the principle of first law of thermodynamics. You can see the manifestation of principle of first law of thermodynamics in heat engine. Okay, so what exactly is a heat engine? Like, engine is something which produces work. Okay, it takes heat and produces work. So engine is something that produces work. Okay, so here you supply heat and you get work. Okay, so heat is nothing but your chemical energy. Okay, heat is chemical energy. So you can say anything available naturally, let us say coal or your petroleum products, all are source of chemical energy. Okay, so coal has certain calorific value, petroleum fuels like diesel, petrol, gasoline, all have some calorific value and chemical energy is stored there. But we want mechanical energy. We want to convert that chemical energy to the mechanical energy, uh, uh, because mechanical energy is all that we want. For example, a car or a two-wheeler, you want the wheel to rotate. Okay, you have chemical energy stored in the fuel, either in petrol or diesel, but you want uh, finally mechanical energy. So uh, this can be related to like first industrial revolution. Okay, so prior to that, like in earlier days, people used to use human muscle power to do some work. After that, they started using. After that, they started using animals like horse or bullock carts and all that, because they are more powerful than humans. Okay, so initially they were using their own power. Then they started using animals. So those are like in the Stone Age they used to do that. But with the advent of steam engine, like that steam engine in like first our train was being driven. Train engine was steam engine. So in steam engine, what happens? Um, they generate steam by burning coal. So their coal is the source of chemical energy in steam engine. So there can be two types of engine. One is external combustion engine, one is internal combustion engine. So this actually the steam engine is external combustion engine, means you are the combustion is happening outside. Okay. Whereas in case of petrol engine, diesel engine, these are all internal combustion engine. The heat is getting generated inside only, inside the engine. Okay. So so heat engine is a manifestation of application of first law of thermodynamics. Okay. So some of the salient features of heat engine. So heat engine is a device where system undergoes cyclic process. So in the last class we were telling about cyclic process. So what is a cyclic process? After n number of processes, the system comes back to its original position. So I was talking about this Carnot cycle. This is the pressure and volume diagram of Carnot cycle. So you can see here, it starts from one, goes to two, goes to three, goes to four, and then comes back to one. That means here, whatever was the temperature initially, or whatever was the pressure initially, volume initially, comes back to that. That means if temperature remains same, there is no change in internal energy. That is the point to be noted. Okay. So heat and work, only those two things are interrelated. For example, first law of thermodynamics, what does it say? Del Q is equal to um, del Q is equal to del W by del U. Okay, that's the thing. So as we are saying that the it's a cyclic process. So the working substance, say let us say steam in steam engine, steam is the working substance. Similarly, in petrol engine or in diesel engine, the gas is the working substance. Uh, like in petrol engine, and there is air. You suck the air. Okay, the air in petrol engine in two wheeler we have something called a carburetor. Okay, so it will be kind of a venturi kind of thing, and the air will get sucked in the carburetor during the suction stroke. Then the fuel will get injected to the air, and the fuel gets vaporized because of the constricted passage. There the fuel gets vaporized and fuel get mixed up with the air. So you create a air fuel mixture there. Okay. Once you create a air fuel mixture, then you put a spark there. Once a spark is you are generating a very high temperature. It's a electrical phenomena like a spark plug. It has a positive, it has a negative. You create a spark there and you start the combustion. That is petrol engine. Similarly, in diesel engine, you suck the air, then suction, then you compress the air. You compress the air. Because of compression only, the temperature of air rises to such an extent that if you inject diesel there by means of an injector, then also you will create some like the air fuel mixture. Okay, so this air fuel mixture, which is the working substance in petrol engine or diesel engine. Okay, similarly in steam engine, it is the steam is the working substance. Okay, so that's what I have written here. There are two types of engine. One is called your internal combustion engine, that is the petrol engine and diesel engine, because the combustion is happening inside. So you can see like the this picture actually. So you can see this is your cylinder, this is your piston, and this is your working substance. So in an internal combustion engine, some gas will be your working substance. So what is I am just showing the power stroke. Okay, this pistons moves inside and outside. Actually, and there are two-stroke engine and there are four-stroke engine. So two-stroke means like four processes gets completed in two-stroke. Okay. So like say this is it goes to this extreme position, and then it comes back to this extreme position. So this movement from this to this is one stroke. Then it will be then movement from this to this is another stroke. So if all suction, compression, and then power and exhaust, there are four things happening. If everything happens in two stroke, like just go uh, 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 from movement from this to this, from the to the extreme position of the piston. If it happens like this, then that is one stroke. Then coming back is another stroke. Okay. So what happens actually this in two stroke, that means one revolution. So what is happening? This is your piston. Sorry, cylinder. Okay. This is your piston. So your piston is going up and down. Okay. So and this is called a connecting rod actually. This is a connecting rod, and this is a shaft. Okay. Shaft, you imagine this is a circle, means the shaft is something like this. Okay. So in case of a crankshaft, the crankshaft will be the crankshaft will be something like this. So no need to go into detail of that. So you just remember shaft is something which is a rotating like kind of rod or whatever. So this is shaft. Okay, so this is your cylinder, this is your piston, and this is your connecting rod, and this is your shaft. This shaft you are not able to see here. Okay, so this is the shaft. Okay, this is the shaft. When you see from the top, this is your shaft. Okay, so this shaft is the wheel is mounted on this shaft. So finally, this wheel rotates, and you get the rotational kinetic energy. The rotational kinetic energy is nothing but a form of mechanical energy. So here, what you have done, like say, you have your working substance, either it is a gas or steam or whatever. So that gas, you get chemical energy from the fuel, and that chemical energy has got converted into mechanical energy. So that's the principle of a heat engine. So two-stroke and four-stroke, at this stage you may not it may not be required for you like to understand what is two-stroke, four-stroke, but just remember in one revolution of this shaft, two-stroke gets completed. So for four-stroke engine, it has to have two revolution. Two revolution, all four has to get completed. In four-stroke, two revolution. In two-stroke engine, in one revolution, it will go and come. Like you can see that 180. Okay. So when it is going 180 like this, it will move up. Then another 180, it will move down. Everything. So when all four processes gets completed in two-stroke, it will be more efficient and proper combustion, and so that's why the efficiency of four-stroke engine is better than that of two-stroke engine. Okay. Uh, okay. So heating in a device where system undergoes a cyclic process. So I have explained you what is cyclic process. Cyclic process is a set of processes where the working substance comes back to its original position. So there is no change in pressure, temperature, and volume of that particular substance. So as we know, then so there are examples of heat engine. And I told petrol engine, diesel engine, or steam engine. So, what is the working substance in petrol engine and diesel engine? It's mixture of fuel and air. Okay. Similarly, in a steam engine, steam is the working substance. In steam engine, coal is the source which uh, which generates which heats up the water and generate the steam and this thing. Okay. So I was telling like with the when the steam engine was invented first, that is the beginning of industrial revolution where people started using mechanical energy, okay, instead of muscular energy. So that is called industry one, okay, industrial revolution, industry one. Then industry two is like the introduction of electronics and those kind of devices. That is industry two. Similarly, after this robots and other things came into picture, like that is called industrial revolution three. Okay, the robots doing the work. Okay, now currently there is a trend for industry 4. So we are going through industrial revolution 4, where a factory is becoming a digital factory. More and more humans are not doing the repetitive work. Machines will do those repetitive work. There will be communication between various machine, communication between machine to human, human to human. Everything will be controlled remotely. You can see things in dashboard and all that. So that is industry 4. So industry 1 started with revolution started with steam engine. That's where people started using instead of human muscular power or the animal power. You may be knowing horsepower. Why we say horsepower? 1 horsepower is equal to 746 watt. Okay. So horse is much more powerful than human. So we used to use horse. That's why horsepower. Okay. So petrol engine, diesel engine, and steam engine. Okay. So one of the so here you can see you can see the pictorial representation of a heat engine. Okay. So you can see there is a heat reservoir. Okay. So there is a heat reservoir at temperature capital T1. That is the absolute temperature. Okay. The absolute temperature T1, and this is your working substance. Okay. At the middle, this is your working substance. So this working substance takes some heat Q1 from a reservoir at temperature T1, and it cannot use convent there when we study the second law of thermodynamics, it's the nature's law, it's the nature level. Whatever you do, the efficiency can never be 100%. Okay, so you cannot convert all the heat energy into work. So some amount of heat has to go to the reservoir. So another, like this is hot reservoir, this is cold reservoir. Another terminology we use for hot reservoir is like say source, heat source, and cold reservoir we can say heat sink. Okay, so this is source, this is sink. So you take heat E1, you do some work W, that work is done on the environment. Okay, so you do some work W, and you have to throw away some heat Q2 to the sink. So take heat Q1 from a reservoir at temperature T1, and dump some heat Q2 to a cold reservoir or a sink at temperature T2, and and get some work done on the environment. So here also you are getting some work output. Okay, that work output finally manifested as rotational kinetic energy of the wheel. Okay, so in the last discussion I was telling you like the area under the PV diagram is nothing but work done. So this one I have hatched it. So this one is like the area under this closed cycle is nothing but work done. Okay, so we were telling now work done is equal to P into delta V, right? So that's the work done. Okay, so um, okay, so there is one important concept linked to heat engine, that is called efficiency. Okay, so efficiency is nothing but work output by heat input. Okay, so what you finally want work done, right? So what you give is heat input Q1. Okay, so so always like output by input is called efficiency. Okay, so you want your efficiency to be 100%, but when we talk discuss about second law of thermodynamics, it the law of nature is such that you cannot convert the whole heat input into work output. Okay, so that's why there is efficiency associated with everything. Okay, so that's the efficiency. Heat, like say calorific value. So what is Q1? Let us say you are using 1 liter of petrol. Okay, so the calorific value of petrol, whatever it is in calorie or kilocalorie or converted to joule, that will be your Q1. Okay, that is the input. Okay, then output is whatever mechanical energy or rotational energy finally you get, and that is your output. Okay, so you get those output like you are saying. Okay, my uh, like engine power is this much. Okay, that means my engine can deliver. Let us say I am saying my engine is a 1 HP engine. That means it can produce 746 joule per second. Okay, that means 746 watt it is producing. So that much of energy is the work output. So that work output divided by heat input. Okay, so that is what you can convert it into joule if you for a certain duration you are using. Suppose you have spent 1 liter of fuel, for how much distance you are able to go. Okay, so that not distance for how much time. Okay, so for suppose you with 1 liter you have traveled 1 hour. So per second, how much power you are producing, and per 1 hour, how much total work, that power into the duration, you can get the work done. That will become joule by joule. So you need to be unit consistent. Okay. So you are getting the work output. You can like 1 liter of petrol, how much of work I have got, you can calculate. You will have a dashboard, you can calculate all that. And heat input anyway, you know, okay, this is the calorific value of 1 liter of petrol or diesel. So with that, you can find out the efficiency of any kind of heat engine. So in general, the petrol engine, diesel engine, steam engine, all these engines, engine is something which gives work, takes heat, gives work. So any petrol engine, diesel engine, steam engine, all are heat engine only. Okay. Why it is called heat engine? Because it takes heat. Okay. It takes heat and gives work. Engine is something which gives work. Takes heat, gives work. Okay. So um, so we told that efficiency is equal to work output by heat input. And with the first law, what does it tell? Heat input is equal to work done plus change in internal energy. But here internal energy does not change because it's a cyclic process. That's why for a closed cycle, del U is 0. Okay. If this becomes 0, del Q becomes equal to del W. Okay. So del W. Okay. So what is del Q here? Because the work done is equal to, you are taking some heat and you are throwing away some heat. So Q1 minus Q2 is the net heat you have taken. Okay. You are not able to use the complete, you are taking Q1, but some amount of heat you are rejecting to the sink. Rejecting means you are throwing away to the sink. That is the law of nature. You cannot avoid it. Okay. Some amount of heat has to be thrown to the surrounding. That's the second law. When we discuss second law, we'll discuss about it. So Q1 minus Q2 you are taking. Uh, so Q1 minus Q2 is equal to W. Okay. So efficiency is equal to W. You replace it by Q1 minus Q2. So it becomes Q1 minus Q2 divided by Q1. Okay. So this finally becomes 1 minus Q2 by Q1. Okay. So so if Q2 is equal to 0, efficiency will become 1, which is never possible. Q2 cannot be 0. Okay. So that's all about heat engine. So I have given an example of a Carnot cycle actually here. This Carnot cycle has two isothermal process and two adiabatic process. So this is a PV diagram. Actually, this PV diagram can be converted into a TS diagram. It will be required in engineering. At this stage, it is not required. That PV diagram or otherwise can be converted into a temperature and entropy diagram. Temperature entropy. Okay. So just for your reference purpose, just remember at this stage, this PV diagram will look like this. And in TS scale, it will look like this. Okay. So it will be 1, 2, 3, 4. Okay. So actually like P into V is work done. Similarly, T into delta S is heat. Okay. So the first from 1 to 2, the area under this curve is Q1. Okay. Similarly, from 3 to 4, the area under this curve is Q2. Okay. So this green area, hatched area, that is Q1, and this blue hatched area, that is Q2. So the net heat Q1 minus Q2 is actually this. This is your net area under this rectangle is nothing but your Q1 minus Q2, which is nothing but your work done. So this Q1, this area is Q1 minus Q2. This area is also Q1 minus Q2 is the work done. So this is the Carnot cycle in PV, same Carnot cycle in TS. Just remember, S is something called entropy. So these two are actually isothermal process. So why it is a horizontal line? Because the temperature remains constant in isothermal. So from 1 to 2, temperature remains constant. That's why it's a horizontal line. Similarly, the 2 to 3 and 3 to 4, 2 to 3 and 4 to 1, that is a adiabatic process. So adiabatic process, there is no heat input. Okay. Yes, so Q external is equal to 0 for 2, 3 and 4, 1. That's why that's an adiabatic process. Ideally, it is a isoentropic process. Like isothermal, there is something called isoentropic. So there is no addition of heat, there is no change in entropy. Okay. So entropy is a measure of randomness or whatever. So if you are not introducing any heat or anything, then entropy remains constant. Okay. So that T into delta S. Okay. So like say it will be like let us say T1 minus let us say T1 minus T4 into your delta S. Okay, that's the that's the heat means Q1 minus Q2, which is nothing but a variable. So just for your reference, like how does a PV diagram of a Carnot cycle looks in TS diagram, but at this stage maybe entropy is not required for uh, your class. Okay. So that's about heat engine. So some key takeaway from this heat engine is a example of application of first law of thermodynamics. That's one. Then heat engine is something which takes heat and gives work. All the heat cannot be converted into work. That's why efficiency will be always less than 1 or less than 100%. You have to throw away some heat to the sink. That's because of second law of thermodynamics. So we'll be discussing about second law of thermodynamics in the coming classes. And this is heat engine. The reverse of heat engine will be heat pump or the refrigerator. So where instead of giving work to the surrounding, you will taking work from the surrounding. In refrigerator there is a compressor. So the compressor is being driven by a motor. So you are taking work from surrounding and throwing it to the surrounding. That's the reverse in refrigerator or heat pump. So when you are heating a room by using a heat pump, so when the environment is cold, like in cold countries, they may be using heat pump or the blower and all that. So when the surrounding is cold, you are heating it like a heat blower or whatever. That similarly, air conditioning or refrigeration. So here, there you are taking work and like say a refrigerator. So you are making the inside of the refrigerator very cold. How do you maintain it? You are maintaining it by throwing away some of the heat to a comparatively hotter surrounding. That's against the law of nature. See, the inside the refrigerator temperature is very low. You have to throw away some heat from inside the refrigerator to the outside so that you can store your food at low temperature, which will prevent the wastage of food. Okay. So when you are throwing away heat, from low temperature to high temperature, it is against the law of nature. If you are doing something against the law of nature, you have to spend work. So that's why in the refrigerator, you have to take work. Okay. In heat pump or the heat blower, you have to take work and you have to take work. So um, the thing will be completely just reversed. Okay. So instead of giving work, you will be taking work. Okay. So that is the principle of refrigerator and heat pump that we'll be discussing in next class. And then in the further classes, we'll be discussing our second law of thermodynamics. Okay. Thank you.